so we should probably start with what is antimatter?
All right, so antimatter in some sense is the mirror image of matter, you know. So if you look, everything you can touch and feel is made out of particles. First atoms, then nuclei, and nuclei are made of protons and neutrons, and then you have electrons. And now if you just invert the charge of all these particles and keep their mass, then you have antimatter. Okay, that's all.
Okay.
The interesting thing is that when you can make matter and antimatter particles from energy. You know, energy equals mass times the square of the speed of light. And that's the process we are using here to create new particles. And every time we do that, we create a particle and an antiparticle. So this way, the universe always stays the same.
Okay, and what kind of research is going on at Cern about antiparticles and sort of applications of them, maybe?
Well, I mean, first of all, Cern is a place where we do fundamental research. So we ask for the reasons why the universe is like it is and so on. So we are not first of all aiming at applications. So it's first of all, it's the question, why did the antimatter apparently disappear in the very first stages after the Big Bang? Because we don't see any of the antimatter which should be there in the universe. So there must be a reason. And the research going on here is to look into two different areas of antimatter physics. One is to make a so-called B quark and an anti-B quark in one of the LHC experiments and look if the decay properties are slightly different. That could give us a hint why the universe is so lopsided nowadays. You know? The other possibility is to make an anti-hydrogen atom and compare it with a hydrogen atom to very, very high precision. And if we can find even the slightest difference between the two, that would be a very important discovery, because theoretically they should be absolutely identical. So these are the two big research applications which go on here. One is the LHC, the other one in the antimatter decelerator, the AD facility. Now, on applications, as I said, we are not here in order to find applications for this kind of research. But inevitably, every time we try to push the limits of technology to do these experiments, we find new ways to do things. And these new ways sometimes have important applications. Like the World Wide Web was an application which came out of Cern. Now, antimatter in the early 70s, we helped produce one of the first positron emission tomography apparatus, which is now used in many, many hospitals, PET scanners. Now, we have been looking into new ways of detecting gammas from annihilations, which we study at the LHC, and we have developed crystals which can do that better than before. And these crystals will also be used in future PET scanners. So that's one application for medical diagnostics. Which is
okay. So can it be used as an energy source perhaps in the future?
Well, this is an answer which is easy. The answer is no. Yeah? Energy sources do not really exist. The only real energy source of the universe was the Big Bang in some sense. But after that, energy is conserved, and maybe even the Big Bang energy is conserved, but now energy is conserved, and that means when we make antimatter, we have to invest energy, and the best we can hope for is to get this energy back. But it's even if we worked with 100% efficiency, it would not be more energy at the end than before.
Okay.
The reality is that we need 1 billion times more energy to make it than we get back. So it's a very big energy sink, actually, not a source. So antimatter will never be an energy source.
Okay. Yeah, so there's obviously a lot of research going into, as you said, anti-hydrogen atoms and trying to find discrepancies between them and hydrogen atoms. And I know they're doing research into the effects of gravity on matter and antimatter. What kind of effects are you hoping to see there?
Well, I would say any difference between matter and antimatter in any respect would be really, really an important discovery.
Do you expect to see a difference at that?
Well, I think some people hope that there is one. You know, theoretically, there is no basis that we should expect one, because there are very fundamental theorems, which is called the CPT theorem, which you can prove on the basis of very general assumptions, and that predicts that matter and antimatter, the static properties of matter and antimatters in the mass, the charge, and so on, should be absolutely identically equal to any amount of precision. So there we would not expect any effect. Gravity, it should also be the same, basically, because there is a so-called equivalence principle, which says mass is energy and energy gravitates. And if it's mass or mass of a particle or antiparticle, doesn't matter, or antimatter. And so it should both fall with the same gravity, with the same acceleration. But who knows? We only know what we have measured and we have observed, and so maybe there is a difference which we don't know of, and then it would be a big surprise and it would be great.
Yeah. Okay, well that's all my questions. Thank you very much.
Pleasure.